Well, folks, today we're going to be exploring and looking at volcanology, the study of volcanoes. And here you see three pictures of three different types of volcanic eruptions. This one here where you have the very violent explosive action which looks in the distance like a hydrogen bomb. The mushroom cloud, the shock wave secondary level here, and down here we have like what we commonly see at Kilauea in Hawaii. We have a continuous flow of magma, lava, just flowing down and being caught into basins and sometimes going right into the water. And here we have another type of eruption which is different from the other two. And we're going to talk about that today. And what's all this about? Well, if you'll remember in our last lesson, for those of you joining us on our YouTube audience, we talked a little bit about tectonic theory and plate tectonics and how it is theorized by some geologists, how the crust of the earth, the surface of the earth, acts over great periods of time. And we talked about that in our last lesson, so we're not going to get into that. But what we're going to do today is move into volcanology. Why are we doing this? Because we're considering it in the examination of the Great Flood event of Noah's time. Because all of these scientific things we're investigating are going to play a role in how we assess our hypothesis that we're going to put forth to share with you what kind of mechanisms we believe the Lord may have used in order to bring about such an event as was described in the scriptures as the great catastrophic flood of Noah's time. We're also going to read to you some ancient, from the antiquities, landscape accounts, one being Jasher, which is very good. It's got quite a bit of information descriptive about what went on with Noah in particular, his family, what they experienced by description as the ark itself was being lifted up by the torrent waters. And we're going to get into quite a few things here. You do have to have the science in order to understand the hypothesis that we're going to put forth. And of course, we're going to say right now, and remind you again, God can do this any way He wants to. His technology is so far above ours that we can't even begin to comprehend just the smallest parts of how He put things together. But we're going to be talking about the geophysics, geomechanical mechanisms that were at play. And this class is our syllabus class for CTS 101-06. That's how we identify this class, primarily dealing with volcanology. So let's get into it right quick. Try to get through with this stuff so we can get on with the story later. About volcanoes. Excuse me. I had to apologize for my voice today, folks. I have some kind of allergy reaction. I can barely breathe, much less talk. About volcanoes. Volcanology, the science of study of volcanoes, and also is the study of lava, magma, and related geological, geophysical, geochemical phenomenon related to volcanoes. The term volcanology is derived from the Latin word Vulcan. Vulcan was the ancient Roman god of fire. Of course, we know that that's not a real god. It was only one god, this god little g here. But anyway, in literature, that's what the Romans attributed volcanoes to be, part of the action of their god of fire, Vulcan. Anyway, moving on. A volcanologist is a person who studies the formation of volcanoes and their current and historic eruptions. Volcanologists frequently visit volcanoes, especially active ones, to observe volcanic eruptions and collect eruptive products, including tephra. I guess is the way you say that. It's hard to pronounce that. T-E-P-H-R-A. Tephra, which is ash or pumice, rock and lava samples. Part of the science is also the study in being able to predict eruptions and predicting earthquakes, which, if successful, would be able to save many lives in advance of such events. Types of volcanic eruptions. Volcanic eruption and volcanic eruptions, we have three basic types that we're going to talk about here in a minute. The Flinian eruption column, the Hawaiian Pahoehoe flows, and the Strombolian eruption. The Hawaiian Pahoehoe flows, often shortened to Hoho, are the flows that just seem to, you can stand by them and watch them go by. They just flow in a continuous flow, building up island structures and things like that. Not always in a violent eruption, but sometimes just pumping out a fresh flow of liquid molten lava. During a volcanic eruption, lava, tephra, which is the ash, the peli, volcanic bombs, and blocks and such thrown out by the volcano, and various gases are expelled from a volcanic vent or fissure. Several types of volcanic eruptions have been distinguished by volcanologists. These are often after famous volcanoes where that type of behavior had been observed, what type of event, etc. Some volcanoes may exhibit only one characteristic type of eruption during a period of activity, while others may display an entire sequence of types, all in one eruptive series. There are three different metatypes of eruptions. So we're going to talk about three different types of eruptions here. The most well observed are the magmatic eruptions, which involve the decompression of gas within magma that propels it forward. Then we have the threatomagnetic eruptions. Threatomagnetic eruptions, I sound like I said that with a T, I'm sorry, or another type of volcanic eruption, driven by the compression of gas with magma, the direct opposite of the process powering magnetic activity, magmatic activity. Sound like I said magnetic, excuse me again. The last eruptive metatype is the phreatic eruption, phreatic, which is driven by the superheating of steam by contact with magma. These eruptive types often exhibit no magmatic release, instead causing the granulation of existing rock. Within these defining eruptive types are several subtypes of volcanoes. So see, it's not just one type of volcano. A lot of folks didn't know that, so we're talking about that a little bit today. The weakest are, as far as eruptive energy release, are the Hawaiian and the submarine. Then the Strombolian, followed by Vulcanian and the Circean. The strongest eruptive types are the Pelian eruptions, followed by Pelian eruptions. In other words, so one right after the other, series in sequence. The strongest eruptions are called ultra-Plinian, Subglacial and phreatic eruptions are defined by their eruptive mechanism and vary in strength. An important measure of eruptive strength is remember this one, this is what scientists use to measure the strength of a volcanic eruption, is the Volcanic Explosive Index. The acronym for that is VEI, the Volcanic Explosive Index. And a magnitudic scale ranging from 0 to 8 that often correlates to eruptive types. You might kind of relate this sort of to like the Richter scale for measuring the intensity of earthquakes, which we're going to get to earthquakes later. Eruptive mechanisms. Volcanic eruptions arise through three main mechanisms, and here they are. Gas release under decompression causing magmatic eruptions. Thermal contraction from chilling on contact with water causing a phreatomagmatic eruption or eruptions. That's an interaction type of eruption between the magma and the water. Ejection of entrained particles during steam eruptions causing phreatic eruptions. There are two types of eruptions in terms of activity: explosive eruptions and effusive eruptions. So these are two types. Explosive eruptions are characterized by gas-driven explosions that propels magma and tephra. Effusive eruptions, meanwhile, are characterized by the outpouring of lava without significant explosive eruption. So the one in Hawaii that we talked about, Kilauea, would be more of an effusive type eruption. Excuse me. Volcanic eruptions vary widely in strength. On one extreme, there are effusive Hawaiian eruptions, which are characterized by lava fountains and fluid lava flows, which are typically not very dangerous. On the other extreme, the Plinian eruptions are large, violent, and highly dangerous explosive events. Volcanoes are not bound to one eruptive style and frequently display many different types, both passive and explosive. Even the span of a single eruptive cycle, volcanoes do not always erupt vertically from a single crater near their peak. Either some volcanoes exhibit lateral and fissure eruptions. Notably, many Hawaiian eruptions start from rift zones, and some of the strongest Surtean eruptions, develop along fracture zones. Volcanic Explosive Index. Remember, we talked about that a little bit. The Volcanic Explosive Index, commonly shortened to VEI, is a scale from 0 to 8 for measuring the strength of the eruptions. It is used by the Smithsonian Institute's Global Volcanism Program. In assessing the impact of historic and prehistoric lava flows. It originates in a way similar to the Richter scale for earthquakes. And I already kind of covered that way, but we'll go over it. In that each interval in value represents a tenfold increase. Now, every time the number goes up by 1, that's what you need to remember. It's like multiplying the strength and intensity, the energy release, times 10. So from one number to the next is a tremendous increase. It's like if this was, say, a 5, and then we went to a 6, it would be 10 times as powerful. Isn't that amazing? It is logarithmic. The vast majority of volcanic eruptions are the VEIs between 0 and 2. In other words, down lower numbers. Magmatic eruptions. Magmatic eruptions produce juvenile clast during explosive decompression from gas release. Now, it's not talking about a juvenile delinquent there. This is just a term we're going to get into here a little bit. They range in intensity from the relatively small, especially the juvenile, fountains on Hawaii, to the catastrophic ultra-Fenian eruption columns more than 30 kilometers or 19 miles high, bigger than the AD 79 eruption that buried Pompeii. Hope all of you can see this okay. Hawaiian eruption. Hawaiian eruptions are a type of volcanic eruption named after the Hawaiian volcanoes with which this eruptive type is hallmarked. Hawaiian eruptions are the calmest types of volcanic events, characterized by the effusive eruption of very fluid basalt-type lavas with low gaseous content. The volume of ejected material from Hawaiian eruptions is less than half of that found in other eruptive types. Steady production of small amounts of lava builds up the large, broad form of a shield volcano. Eruptions are not centralized at the main summit, as with other volcanic types, and often occur at vents around the summit and from fissure vents radiating out of the center. Hawaiian eruptions often begin as a line of vent eruptions along a fissure, so-called curtain of fire. These die down as the lava begins to concentrate at a few of the vents. Central vent eruptions, meanwhile, often take the form of a large lava fountain, both continuous or sporadic, which can reach heights of hundreds of meters or more. The particles from lava fountains usually cool in the air before hitting the ground, resulting in the accumulation of incendiary scoria fragments. However, when the air is especially thick with clasts, they cannot cool off fast enough due to the surrounding heat and hit the ground still hot. The accumulation of such forms splatter cones. If eruptive rates are high enough, they may even form splatter-fed lava flows. Hawaiian eruptions are often extremely long-lived. A cinder cone of Kilauea has been erupting continuously since 1983. That's a long time for continuous flow of lava. That's how the Hawaiian Islands were built up out in the Pacific Ocean, was by these volcanic actions. Another Hawaiian volcanic feature is the formation of active lava lakes, self-maintaining pools of raw lava with a thin crust of semi-cooled rock. There are currently only 5 such lakes in the world, and the one at Kilauea's vent is one of them. We're getting there, folks. Got to work through some of this science before we can talk about the causes of Noah's flood. Kilauea flows from Hawaii's eruptions are basaltic and can be divided into 2 types by their structural characteristics. Pahoehoe lava is a relatively smooth lava flow that can be billowy or ropey. They can move as one sheet by the advancement of toes, or as a snaking lava column. Lava flows of the A type flows are denser and move viscous than Pahoehoe, but tend to move slower. We'll get into this a little bit here, but some of this is more deeper description, so we don't really need to necessarily get into for the purposes of our discussion in our study. Flowing can measure 2 to 20 meters, 7 to 66 feet thick. A flows are so thick that the outside layers cools into a rubble-like mass, insulating the still hot interior and preventing it from cooling. A lava moves in a particular way. The front of the flow steepens due to the pressure from behind until it breaks off, after which the general mass behind it moves forward. Pahoehoe lava can sometimes be, this is kind of explaining what its characteristic is here. Pahoehoe lava can sometimes become A's lava due to increasing viscosity or increasing rate of shear. But A's lava never turns into Pahoehoe flow. Excuse me. Hawaiian eruptions are responsible for several unique volcanical objects. Small volcanic particles are carried and formed by the wind, chilling quickly into teardrop-shaped glassy fragments known as Pele's tears, after Pele, the Hawaiian volcano deity. Another one of these demigods, Pele. The ancients had all kinds of superstitions. Carried over even into modern time. During especially high winds, these chunks may even take the form of long, drawn-out rods, known as Pele's hair. Sometimes basalt aerates into reticulite, the lowest density rock type on Earth. Basically what you're looking at when you look at this dark black lava-looking stuff, it looks like a black sponge. Although Hawaiian eruptions are named after the volcanoes of Hawaii, They are not necessarily restricted to them. The largest lava fountain ever recorded formed on the island of Izu-Ishima on Mount Mahara in 1986, a 1,600-meter, 5,249-foot gusher that was more than twice as high as the mountain itself, which stands 764 meters, 2,507 feet high. Volcanoes known to have Hawaiian activity include, well, we'll skip that part for right now. You can look that stuff up online. Let's move on. Let's go on now, and let's talk about the Strombolian types of eruptions. We talked about Hawaiian lava flow style eruptions. Now let's look at the Strombolian eruption. Strombolian eruptions are a type of volcanic eruption named after the volcano Stromboli, which has been erupting continuously for centuries. Strombolian eruptions are driven by the bursting of gas bubbles within the magma. These gas bubbles, often the magma, accumulate and coalesce into large bubbles called gas slugs. These grow large enough to rise through the lava column. Upon reaching the surface, the difference in the air pressure causes the bubble to burst with a loud pop, throwing magma in the air in a way similar to the soap bubble. Because of the high gas pressures associated with the lavas, continued activity is generally in the form of episodic explosive eruptions, accompanied by the distinctive loud blast during eruptions. These blasts occur as often as every few minutes. The term Strombolian has been used indiscriminately to describe a wide variety of volcanic eruptions, varying from small volcanic blasts to large eruptive columns. In reality, true Strombolian eruptions are characterized by short-lived and explosive eruptions of lava and intermediate viscosity, or with intermediate viscosities. Often ejected high into the air, columns can measure hundreds of meters in height. The lavas formed by Strombolian eruptions are a form of relatively viscous basaltic lava, and its end product is mostly scoria. It's a type of deposit. The relative passive of Strombolian eruptions and its non-damaging nature to its source vent allow Strombolian eruptions to continue unabated for thousands of years, and also makes it one of the least dangerous eruptive types. Good to know. Strombolian eruptions eject volcanic bombs and lapilli fragments that travel in parabolic paths before landing around their source vent. The steady accumulation of small fragments builds cinder cones composed of completely basaltic pyroclasts. This form of accumulation tends to result in well-ordered rings of tephra. Strombolian eruptions are similar to Hawaiian eruptions, but there are differences. Strombolian eruptions are noisier, produce no sustained eruptive columns, do not produce some volcanic products associated with Hawaiian volcanism, especially Pele's tears and Pele's hair. They produce fewer molten lava flows, although the eruptive material does tend to form small rivulets. Volcanoes known to have, we're going to skip over the descriptions of which volcanoes are like that right now. You can look those up online. For our purposes, we can move on. Let's see here. I think we're going to start. I'm going to talk about Pelian eruptions. Pelian eruptions are characterized most prominently by the incandescent pyroclastic flows that they drive. The mechanics, that's one of the pictures we looked at a while ago, were real bright. The mechanics of a Pelian eruption are very similar to that of a Vulcanian eruption, except that in Pelian eruptions, the volcano structure is able to withstand more pressure. Hence, the eruption occurs as one large eruption rather than several smaller ones. Phreatomagmatic eruptions. The phreatomagmatic eruptions, that's a difficult word, are eruptions that arise from interactions between water and magma. You can imagine what happens when you hit that water with that hot magma. They are driven from thermal contraction, as opposed to magmatic eruptions, which are driven by thermal expansion. Difference is contraction versus expansion with the phreatomagmatic eruption, as opposed to magmatic eruptions, which are driven by thermal expansion of magma when it comes in contact with water. This temperature difference between the two causes violent water-lava interactions that make up the eruption. The products of phreatomagmatic eruptions are believed to be more regular in shape and finer grained than the products of magmatic eruptions because of the differences in eruptive mechanisms. Now there's a term right there that we're going to keep all the way through our discussions when we're talking about all the events of the cataclysm during the flood event of Noah's time. Mechanisms. In this case, it's eruptive mechanisms. There's going to be a lot of geophysical mechanisms at work. Some astrophysical as well. There is debate about the exact nature of phreatomagmatic eruptions, and some scientists believe that fuel-coolant reactions may be more critical to the explosive nature than thermal contraction. Fuel-coolant reactions may fragment the volcanic material by propagating stress waves, widening cracks, and increasing surface area that ultimately lead to rapid cooling and explosive contraction between the eruptions. Circean eruption, or hydrovolcanic, is the word I like to use, is a type of volcanic eruption caused by shallow water interactions between water and lava. Named so after its most famous example, the eruption and formation of the island of Circe off the coast of Iceland in 1963. Circean eruptions are the wet equivalent of ground-based Strombolian eruptions, but because of where they are taking place, they are much more explosive. This is because as water is heated by lava, it flashes into steam and expands violently, fragmenting the magma it is in contact with into a fine-grained ash. Circean eruptions are the hallmark of the shallow water volcanic oceanic islands. However, they are not specifically confined to them. Circean eruptions can happen on land as well, and are caused by rising magma that comes into contact with an aquifer, water-bearing rock formations, an aquifer, at shallow levels under the volcano. The products of the Circean eruptions are generally oxidized basalts through andesitic eruptions do occur, albeit rarely, and like Strombolian eruptions, Circean eruptions are generally continuous or otherwise rhythmic. A distinct defining feature of the Circean eruption is the formation of a pyroclastic surge, or base surge, a ground-hugging radial cloud that develops along with the eruption column. Base surges are caused by the gravitational collapse of a vaporous evaporative column. Isn't that neat? One that is denser overall than a regular volcanic column. The densest part of the cloud is nearest to the vent, resulting in a wedge shape. Associated with these laterally moving rings are dune-shaped depositions of rock left behind by the lateral movement. These are occasionally disrupted by bomb sacks, rock that was flung out of the explosive eruption and followed by a ballistic path to the ground. or following a ballistic path to the ground. Accumulations of wet spherical ash, known as ascensionary palei, is another common surge indicator. You're getting there. Over time, surges and eruptions tend to form maars, broad, low-relief volcanic craters dug into the ground, and tuff rings, circular structures built of rapidly quenched lava. These structures are associated with a single vent eruption. However, if eruptions arise along fracture zones, a rift zone may be dug out. These eruptions tend to be more violent than the ones forming a tuff ring or maars. An example being the 1986 eruption of Mount Tawaria. Littoral cones are another hydrovolcanic feature generated by the explosive deposition of basaltic tephra, although they are not truly volcanic vents. They form when lava accumulates within cracks in lava, superheats and explodes in steam explosion, breaking the rock apart and depositing it on the volcano's flank. Consecutive explosions of this type eventually generate the cone. Now, before we go, a quick question. Does anybody know where the largest volcano known to man is? The largest volcano ever known, ever photographed, or ever seen? Nobody? Come on. It's on Mars. Mount Olympus. Mars Olympus on Mars is the largest volcano in the entire solar system, as far as we know, from photographs we've took so far. Well, guys, we're going to be moving on in our next class. We've got a couple of more subjects of science that definitely have to be looked at. We're going to be looking at some meteorology, things that we need to know about the Earth's atmosphere, is how its hydrocycle works. We're also going to look at a little bit about the moisture content, vapor content of the atmosphere. We need to know that when we're talking about something like a 40-day rainstorm. And we're going to look at a little bit about storm theory, but not a whole lot, just enough to fill you in a little bit. And we're also our last part of our discussion is going to be on gravity and gravity's effect upon things on the Earth and in the Earth. Gravity doesn't, let's just use, for example, the moon. The moon, as it circles the Earth, we know it has a tidal effect on the oceans. Well, there's also tidal effects on things inside the Earth that are also molten or liquid, such as the ethosphere and all of that inside, the molten magma, the upper and outer core. All these things are affected by tidal effects from gravity. So any gravitational object moving nearby to Earth would have a tremendous effect on several things. We're going to talk about all that. But after we have a couple of more classes dealing with some sciences, some basic sciences, just for some familiarization, we're going to move into the literary examination of the events of the cataclysm of Noah's day, the Great Flood. Some of the things that were going on in what literature describes. And you'll already have the science, and then we're going to put it all out on the table. And together we're going to hypothesize what we believe actually were the mechanisms at play during the flood, what caused it, what allowed for it to happen, how it happened, how it was sustained. That's one of the biggest things, how such a thing could be sustained for 40 days. Well, enough about volcanoes for today. Go. End of class session. Go. You are dismissed. Come back again for our next class, which is 101-07. And we'll be moving into some thoughts about meteorology. Have a great day. God bless you.